So next we're going to take a look at an example on the command line of just regular PIM in sparse mode. And essentially what we're going to be doing here is that we have our MPLS layer 3 VPN network in the middle, which is routers 1, 2, 3 on the bottom and XR 1, 2, 3 at the top. I do already have them configured for profile 0 for the multicast VPNs. So at this point we're not going to focus on the core of the network. We're simply going to assume that a PIM packet goes in, PIM packet comes out on the other end, and effectively from the customer's point of view, this is going to be working transparently. Okay, so specifically, let's go ahead and label what's going on here in the network. We have the MPLS network that is going to be made up of these 6 nodes. Okay, so from the point of the customer's, from the perspective of the customer, this is going to look like a cloud. So we have a multicast packet go in. Multicast packet is simply going to come out on the other end. Okay, today we're going to look at the specifics of, well, how do we get it to come in on one side and then pop out the other side? This is going to be the MVPN profiles that we're going to be running over the layer 3 VPN. Okay, specifically the MPLS layer 3 VPN. Okay, so the first step we would need to do for regular multicast routing is we need to turn multicast routing on. Okay, so let's start at the bottom left portion of the network. Okay, and like I mentioned, most of this is pre-configured just to save us some time, but I want to talk about what these steps would be. So in global config, we first turn on IP multicast routing. Okay, it depends on the platform. There may be some arguments after this. You need to say distributed on this particular platform. Then on the physical interfaces towards the other neighbors, we're going to enable IP PIM in sparse mode. Okay, same thing on the other end of the link. So on router 5 globally, IP multicast routing, distributed. Okay, on gig 2.56, IP PIM is running in sparse mode. Okay, from router 5, if we look at the show IP PIM neighbors, the next step is we would want to make sure that they form an adjacency. And we can see that router 5 has an adjacency to router 6, and it has one that's already been pre-configured over towards router 1. Okay, so let's go to the other devices outside the provider network. So from router 4's point of view, show IP PIM neighbors. We should have 2 neighbors. We should have router 8 and we should have XR1. Then router 9 should have 1 PIM neighbor. It should have XR3. Show IP PIM neighbors. Okay, we have XR3. And then on the bottom right, we should see that router 7 has 1 neighbor, which is router 3. Show IP PIM neighbors. Okay, PIM neighbors are up. Okay, now again, assuming that we're running regular sparse mode, this means that the receiver is going to signal with an IGMP version 2 join message. That means we don't know about the sender, but we do know about the receiver. Now once that message comes in, the report, the first top router connected to, or the last top router, depending on how you want to say it, last top router connected to the receiver is going to send that message towards the rendezvous point, so up the tree as a PIM message to the RP saying, hey, I have a receiver. Okay, the problem though is that if we don't know who the rendezvous point is, we don't know where to send this message. Okay, so in this particular design, we're going to say that router 5 is going to be the rendezvous point. Okay, a number of different ways that we could do this. We could go to all of the devices that are in the PIM domain, and we could just say IP PIM RP address 5555. Okay, so we could specify router 5's loopback. Disadvantage of this though is that we have a lot of points to edit. Okay, we could also run auto RP, okay, which is the Cisco version of doing a dynamic assignment. Or if we had the option, we would prefer to use Bootstrap router, which is effectively the IETF or the standardized version of auto RP. Okay, so on router 5, next thing we need to do is enable PIM on its loopback, because we're going to be using this address to advertise the bootstrap router and to advertise the RP candidate. So if we show run, actually let's just go to global config, interface loopback 0, IP PIM, sparse mode. And globally, IP PIM RP candidate. Okay, what interface are we advertising? We're advertising our loopback. And IP PIM BSR candidate, loopback 0. Now the BSR messages are encoded directly inside of PIM, where the auto RP messages, they have a separate control plane, which is the groups 224.0.1.39 and 224.0.1.40. You run into kind of a chicken and the egg problem with auto RP, that until you advertise these control plane groups everywhere, you're not able to build the tree to learn about the RP. But in order to build that tree, you need an RP to send a register message to. Okay, the workaround for this originally was to run PIM in sparse dense mode, but most of the platforms don't even support dense mode anymore. So the workaround for this would be the IP PIM auto RP listener command. The other issue now, though, is that we would need to issue that command everywhere. So as opposed to using auto RP, which we're going to have to touch every single node anyways, okay, we might as well just do a static assignment at that point. This is the reason why we're using BSR. BSR is really plug and play. As long as the PIM neighbors are already established, we just say those two commands, IP PIM BSR candidate, IP PIM RP candidate, and then we advertise whatever source address into the rest of the PIM topology. Okay, so let's now look at the show run pipe include PIM. Okay, so we have PIM sparse mode on the interfaces, plus we have the BSR candidate and we have the RP candidate. Okay, next thing we want to check is, did router 6 learn about this advertisement? So we want to show IP PIM, show me the rendezvous point mappings. Okay, in this case it says we did learn about the rendezvous point. Okay, rendezvous point is 5555. Oop, pen's not working. Okay, rendezvous point is 5555. And it says we learned this from the information source 5555, which means the bootstrap router. Okay, so via bootstrap. Okay, so we know now where to send our join messages to. Okay, next let's look at the other sites and see if they also see this information. So if we go to router 8 and we show IP PIM RP mappings and we see the group address, this means that whatever is going on in the cloud, okay, we're running some type of PIM in the cloud, but we don't yet know the details of it. The idea is that we want that BSR message to go out and then pop out from all of the other sites. So we need to see from router 7, 8, and 9, are they receiving the rendezvous point information? Okay, so on router 7, 7 is in the bottom right. Let's show IP PIM RP mapping. Okay, we do know about router 5. Then same thing on 8 and 9. Okay, show IP PIM RP mapping. We know about the rendezvous point. And then lastly on router 9, show IP PIM RP mapping. Okay, rendezvous point mapping is there. Now before we make any other changes, let's go ahead and create a traffic capture, because we want to know what information does the rendezvous point actually see, and then how is it reacting to build the tree based on this. Okay, so we're going to be capturing on router 5's interfaces, and we want to see what happens when a join message comes in, or what happens when a new sender comes onto the network. Okay, so under viral, we're going to create a traffic capture. So this is going to be on router 3, okay, specifically router 3 interface gig 2. We're going to create a traffic capture. Okay, all of the default options. And now let's go ahead and build the rest of the topology. Okay, next thing we need to do is signal a receiver. So let's say that we have a receiver on router 8. Okay, so on router 8, we're going to say IP IGMP join. And then a multicast group, let's say 228.888. This is now going to be sent as an IGMP report message to router 4. Router 4 is going to say, well, let's look at the group address and figure out who is the rendezvous point that is mapped to this. Okay, rendezvous point's address is 5555. It then says, how do I get to router 5 through a unicast forwarding point of view, which would go this way. So we now send the PIM join message. Okay, so the IGMP message is only going to be locally significant between 8 and 4. 4 is going to turn the IGMP join or the IGMP report into a PIM join. Then it's going to be processed up the tree, hopefully, over to router 5. Okay, the way that we can verify this on router 5 is if we show IP mroute. Okay, if we show IP mroute and look for that particular entry, 228.888, we're trying to find the entry for the receiver, but remember that the receiver doesn't yet have a sender. So in the multicast routing table, this should be a star comma G as opposed to an S comma G. Okay, so first we're going to start on router 5 and make sure that we do not have that entry yet. So on router 5, let's show IP mroute 228.888. Okay, group is not found, which is correct. Okay, next on router 8, we're going to go to our loopback and say IP IGMP join 228.888. Okay, if we were using a source-specific join or an IGMP v3 report message, we could also specify the source. If you are to do this, remember that you need to enable IGMP version 3 because the default value is version 2. Okay, so we're joining the group 228.888. Okay, next let's go to router 5 and look at the same thing again. Show IP mroute 228.888. Notice now that we do have the entry. Okay, if we look at the specific details of what it's specifying here, it says that I know someone is listening for 228.888, but I don't know where that traffic is yet coming from. Okay, that's what null means in either the incoming interface list, meaning I don't know the sender, or if it's null in the outgoing interface list, that means I don't know the receiver, or I'm currently not forwarding. Okay, so ideally we need to connect these two together. We're going to have an entry for the S comma G, which is the sender, and we're going to have an entry for the star comma G, which is the receiver. Okay, next we're going to send traffic. So sender is going to be in the upper right. That's going to be router 9. So we're going to send traffic to 228.888. And we could see based on the topology, if we were to send this traffic over to router 5 first, and then router 5 send it back to router 4, this is kind of an inefficient path. Okay, ideally, we would go directly between 9 and 4, and this is again what we call the shortest path tree switchover, the SPT switchover. So ideally what we should see happen is that we have a unicast register message that goes from router 9 over to router 5. Router 5 takes this packet and it decapsulates it, forwards it as multicast to the destination. Once the destination receives it, which is router 4 in this case, the last hop router, it's going to initiate the switchover to edit router 5 out of the tree. Okay, and the way we do this is simply with a ping. So let's go to router 9. And we're going to ping 228.888, 228.888. Okay, we'll give it a high repeat count. Okay, we did get a reply in. And notice here what changed is that the first packet, it took 34 milliseconds to get there. Packets 2 through 7, they're only taking a couple milliseconds. So this tells us that there was some change in the way that we were forwarding the traffic for the first packet versus the other ones. Okay, so next let's take a look at the traffic capture that router 3 has. Okay, router 5. And router 5, oh, wait a minute. Did I capture this on the wrong box? Yes, I did. I meant to capture router 5. That's okay. Let's do this again with another group. So let's create another traffic capture on router 5. And okay, we're capturing on router 5. Okay, so next, let's go ahead and join another group. Okay, so on router 7, we're going to join 227.777. Okay, again, the pre-verification for this would be to go to the rendezvous point, and on the rendezvous point, we would show IPM route for their particular group. Right now, we should see that there's no entry for this. Next step, router 7 signals that it wants to receive this particular group. IP IGMP join 227.777. Router 5 hopefully says we have the star comma G, which it does. Okay, this means that the customer's multicast signaling is working and the core's signaling is working. Okay, if we look at this from the packet capture point of view, and let's look for PIM. Okay, so here we see the register message. This was router 9 forwarding the packet to 5, saying this is the multicast sender and the sender and the group that we're trying to register. Okay, so notice that even though the packet capture, it says source is 9999, destination 228.888, this is actually a unicast message that is going directly to the RP. So if we look back at the diagram here, this says the source was 9999 and the destination was router 5. Okay, it was that interface on router 9 that did the registering, and we sent this message as a unicast to the rendezvous point. Okay, this is now what is making router 5 install the 9999, 228.888. So 9999, 228.888. Okay, and we can verify that from router 5 by looking at the show IPM route for 228.888. Okay, it says we have two different senders, the loopback and the physical interface address. This is because when I did the ping, I didn't specify what source that I want to send it from. Okay, if you do just a standard ping, it's going to ping out all interfaces. If you do extended, you could say source the traffic from the loopback, for example. Okay, but the point being is this is the end result of the register. Register is saying that if traffic comes in from this device in this interface, currently I'm just going to null route it. Okay, the reason why, again, is that we look at who the receiver was. The receiver was router 8. To get from 9 to 8, 5 is not in the transit path. So only initially, while we're doing the register and then we're doing the switchover, would we see router 5 receiving those packets. Okay, the other portion of this is going to be the IGMP reports. So if we go back to Wireshark, we see the register messages, we see hellos, and then we should see, and also real quick, register stop. This is the acknowledgement. So there was a register message that 13 told 5 and here's the source and here is the group. Okay, router 5 replies, it says, okay, I know about this particular sender, or excuse me, I know about this particular source there, and I know about that particular group. Okay, so that's the acknowledgement register and then register stop. We should see join prune though, which is right here. Okay, so this is saying router 4 wants to be added to the tree. It says the upstream neighbor is 11. This is the source and group pair. So if we look at this back based on the diagram, this is between 11 and 4, which is over here. So router 4 sent the IGMP, excuse me, no, it sent the PIM join. PIM join goes over to XR1. XR1 then encodes this and forwards it towards router 5. Okay, so to recap here, the important point to begin with is that we first establish reachability to the rendezvous point. Because the rendezvous point for regular PIM sparse mode, this is where all of the receivers are going to signal saying, hey, I want to get traffic for this particular group. But the issue is that typically they don't know where the senders are to begin with. Okay, if they did know the senders, that would be PIM in source-specific multicast. So we go to the rendezvous point knows the receivers. Okay, now the sender starts sending its packets in, and we have the register message goes to the rendezvous point. Rendezvous point says, okay, I know that now, send register stop back, and it installs that entry into the multicast routing table. Once there is a match between the star G and the SG, the incoming interface list is populated, or excuse me, the outgoing interface list is populated saying, now I want to take the traffic and actually continue to forward it. Okay, where we would see this would be, for example, on router 4. Router 4 should have both the S, G and the star, G entry. So if we show IPM route for 224.888, group is not found, or 228.888. Okay, incoming interface list is from the provider network. So in from XR1, and then out is gig 2.48. Okay, so we're forwarding in that direction. Okay, right now we don't know about a sender though. Okay, so let's go to router 8, and we will, or actually this is the other way around. No, not router 8. Who was I on before? I was on router 4. Well, router 4 would see the S, G entry as well, so it means that there's no sender right now. So let's go to router 9 and do the same thing. We're going to ping again. The register goes to the rendezvous point, flows down the shared tree to get to router 4. Router 4 now knows about the sender. Okay, so what it does specifically is take both the incoming and outgoing interface list, it gets copied down to the S, G entry, and now we begin to forward. It says anything that came in gig 2.411, this is the sender, this is the group, we need to forward it out this particular interface. Okay, end result hopefully should be that we're receiving the pings back. Because router 8 is the one that signaled the IGMP join. And again, under show run interface loopback 0, We're doing that with just an IGMP join message. There's a question here, is there any reason to run AutoRP instead of BSR? In my opinion, no, because there's extra configuration that you need to use for AutoRP. Really the big issue is going to be, do you already have it deployed, and do you want to continue to support that? Other main issue you run into is interoperability. That some of the other vendors, I believe, support it, but in the vast majority of cases, no, it's a Cisco proprietary protocol.